One of the biggest struggles I see for pilots ranging all the way from student to professional is controlling airspeed and altitude simultaneously. You may have heard statements like pitch for airspeed and power for altitude, or even the reverse of that statement. But these statements are fundamentally incomplete. They don't fully consider the physics of the problem. So today we're going to take up my Luscombe and do some exercises to show the airplane's natural behavior. And from that, we'll be able to come up with a better strategy. So let's get started.
All right, everyone, welcome on board. We've got the Luscombe started. I got the weather, got all my stuff set up, so I think we're ready to taxi out for departure. We got a short taxi this morning here from the ramp to runway 02 at Wahoo, so I'll make that call. Wahoo traffic, Luscombe 903 is on the ramp, taxi 02 Wahoo. So today we've got some flying to do. Go up and look at pitch and power, airspeed and altitude, which is something I've been fascinated with ever since I started flying, and have been studying it for 12 years now. And like I said in the intro, there's lots of debates out there about how this stuff works, but I think if we go out and just let the airplane have its say, I think we'll see some interesting stuff that can help us. So the area is clear. I did a traffic turn earlier, run-up's complete, final lineup checklist. Yep, is done. Winds are basically right down the chute, runway 02, and we'll make our call. Wahoo traffic, Luscombe 77903 is departing runway 02, will be a left turn out to the west, Wahoo. Okay, we got that done. Still don't see anyone, haven't heard anyone, doesn't mean there isn't someone there. So always being careful. Alright, we've got runway 02 identified. Winds are right down the chute. Power's set, instruments in the green, airspeed's alive, tail's coming up pretty quick. Keep it on center, 55, rotate. Oil pressure's in the green, climb rate's good, airspeed's good. Get that head on a swivel. Got a nice overcast layer this morning, which I kind of prefer, cuts down on the haze and the glare. Looking around. Oil pressure, oil temperature still in the green, 65 if I let go. So it trimmed a little fast. There she goes, climbing good. Throttle's not creeping on me. And there's 300 feet below pattern altitude. Pick up the left wing, looking left, clear left, turning left. So we're going to put some conditions on what we're going to do today. We're going to be specifically talking about an airplane in level flight in the air. So no turns, no takeoffs, no landings. We're simply trying to understand how does this machine behave when we change pitch and power with its airspeed and its altitude. And that's all we're looking at. So we can save turning flight, takeoffs and landings for another video. But today we're trying to build a mental model in our head of what does this machine want to do, what does it do when we affect one control, what does it do when we affect both controls, and once we learn from the machine, then we can come up with our strategy. So as we're climbing out here, let's ask the question, why is there so much confusion on this subject? And one of the first reasons is that there's a lot of different flavors of airplanes out there. And different airplanes behave differently. So there is no one single strategy for how to fly all airplanes. I think we're going to come up with a decent strategy, one that I think especially works in piston airplanes, but I fly turboprops and jets for a living, and it works pretty well there too. I can't claim that it works in everything, and I'm not going to try to, but I think you'll find it helpful. And the problem is that the statements that I mentioned also, you know, pitch for airspeed, power for altitude, or the opposite, power for airspeed, pitch for altitude, they're fundamentally incomplete. They don't fully answer the problem. They work some of the time in certain scenarios, but they don't work all the time. And the reason we have those statements is to try and help students as they're coming up through training, to help them learn how to apply proper control inputs. But we kind of shoot ourselves in the foot with those oversimplifications a little bit. I'm going to try and level off here at 3,000. And the problem at the bottom of the barrel is something called causality. And causality, let's just come up with a simple analogy. You know, let's say I work a job for a day and I get paid $100. The reason I have that money is because I worked the job, not the other way around. Right? If I said I have $100, therefore I get to work a job, that wouldn't make any sense. The causality would be backwards, right? So we need to take a look at the airplane and understand what's causing what. And I think you're going to find that interesting today. So we're getting away from Wahoo here, and we're at 3,000 feet. Let me run the cruise checklist, which is pretty simple. Basically set power. My fuel valve is on. Make sure she's trimmed here. Yep, pretty good. Low pressure, low temperature in the green. So the first thing that you have to go to when you start talking about causality and understanding airplanes is the forces, right? And specifically, we know the four forces of flight, right? Lift, thrust, weight, and drag. We all know that. But airplanes create a whole lot more aerodynamic forces than just those four fundamental forces of flight. And so anytime you move a control surface, you're creating force. And if you really want to know how does this airplane behave, you have to go to the forces. And I've done a lot of that, a lot of engineering work in terms of understanding how these airplanes work at the force level. And once you understand that, then you can work up from there. And there's some great books out there if you want to dig into this a little bit more. But the primary force we need to talk about today is the force on the tail that we can create with the elevator. So we have the horizontal stabilizer back there, and we have the elevator. And when we pull back on the stick, right, we tip the aft end of the elevator up. When we push forward on the stick, we tip it down. And with that, we can control the lift that the tail creates. So we're getting far enough away from Wahoo. I'm looking around, the area appears clear. Turn down the radio. And so let's talk about the force that the tail is creating. If I pull back on the stick, we see the nose rise. Why does the nose rise? Well, here we begin with our causality. The nose rises because the tail pulled down. We created lift downward with the tail. If I push forward on the stick and the nose drops, the nose dropped because the tail lifted. The tail created an upward lift, which tipped us over our center of gravity and pitched the nose down. So at the basis of this problem is the force that the tail creates. More lift on the tail, less lift, and then negative lift. Push forward on the stick, the tail is lifting, the tail is pulling down. right? We can see that over the nose. And that's fundamentally what that tail back there is doing. It's creating a force. And that force acts from our center of gravity, which then creates a moment. You know, we talk about moments when we are doing weight and balance. And so we can do that. Now, let's think about how the tail is creating that force. Well, obviously it's an aerodynamic force, and it's primarily acting through these changes through angle of attack. So, like I said, when we push forward on the stick, we tilt the tail down. That is inducing positive angle of attack. When we pull back on the stick, tipping the tail up, that's a negative angle of attack. So we can locally control the angle of attack of the tail back there. Now the cool part about that is, if we're just looking at a wings level airplane system in flight, we have the weight, we have the lift from the wing, which would be acting right about here actually, and then we have the lift of the tail in the back. And when all is balanced, just like a seesaw, right? When the forces balance, seesaw stays steady, right? And so right now, the lift of the wing and the lift of the tail, whatever it is, are canceling each other out, and the airplane is staying in level flight. But when we push on the stick, now we change that force, and now we induce a change in the wing itself too, right? So fundamentally what we're doing when we push and pull with the tail is we're inducing an angle of attack change on the wing. And this is very simple. When you push forward on the stick, you are decreasing the angle of attack of the wing. When you pull back on the stick, you are increasing the angle of attack on the wing. And what is angle of attack? We know that angle of attack is the angle between the wind and the wing, or the relative wind and the chord line of the airfoil. But I like the wind and the wing because it sounds good, right? So we're changing the angle between those two. So the farther back on the stick I pull, the more angle of attack I'm generating on the wing. And you can probably guess, if you've done a little bit of flying before, what will happen if I pull the stick back too far. I'll keep increasing the angle of attack, and the airplane will stall, right? The nose dropped uncommanded there. And believe it or not, the same thing would happen if we were brave enough to push too far forward on the stick. The airplane would stall the other way. Nose down. We do not want to do that, I can tell you that much. Now we've worked our way pretty good from Wahoo here, so I'm going to do a clearing turn to the left, and I'm going to reverse course just so that I don't get too far from the airport here. So fundamentally, what is the stick doing? The stick is inducing an angle of attack change on the wing. The farther back I have the stick, the more angle of attack I have. The farther forward I push the stick, the less angle of attack I have on the wing. And if we push forward enough so that we don't have angle of attack, so that the lift on the wing is zero, and there's some simplification in there, but let's just say zero angle of attack or thereabouts, and zero lift on the wing, we know that we would float over the top, right? So we would go into 0G. And I didn't even get to 0G there, but I pushed a little bit. And if I pull back on the stick aggressively, I increase angle of attack, and the lift of the wing increases until we slow, and there we go. So fundamentally, the tail is creating a force which is acting through angle of attack. Now the next part in the puzzle is very interesting, and it's not something talked about very much, and that is that we as pilots are very good at maintaining 1G. Our bodies love to stay at 1G, right? We sleep all night in our bed at 1G. We walk around, sit in a chair, we're at 1G. Our body knows 1G very well. So if I had a co-pilot with me today and I could close my eyes and they were pitching with the stick, I could tell you, there's positive G, and then float over the top, there's negative G, or 0G, right? I could feel it, and I could tell. And one of the things about pilots is that we are very good at staying at 1G, whether we realize it or not. So, you know, let's say you're pulling. Well, our brain naturally wants to go away from that because our body wants to stay at 1G. So, pilots are 1G maintaining machines. And what that means is we can now go look at the lift that the wing is creating. And what that means is that unless we're aggressively pitching, the wing is always creating lift equals weight, basically, most of the time. It varies a little bit. But pretty much lift is the same, right? I'm going 90 miles an hour here. Lift equals weight. If I speed up and I go maximum speed, lift equals weight. If I pull the power back and slow down all the way just before I stall, lift equals weight. So then we have to ask if we can keep lift constant, or pretty close to it, and we can change angle of attack with the stick, what does that tell us about our airspeed? And if you go through the equations, you end up with a causal relationship that tells you that airspeed and altitude are the opposite of each other. And we can just demonstrate that right now. So if I'm just putting power in so that I don't descend. We'll get into that here a little more later. But if I push forward on the stick, the airspeed increases, the angle of attack decreases. If I pull back on the stick, the angle of attack increases, and the airspeed decreases. So when people say pitch for airspeed, there is truth in that statement, right? I can pull back on the stick, the airspeed decreases. I start pushing forward on the stick, the airspeed increases. And that's because as a pilot, I'm moving the controls slow enough to maintain 1G, and we then have to trade back and forth between angle of attack and airspeed. So now my angle of attack is getting small because I push forward on the stick, which consequently my airspeed grows. And I pull back on the stick, and the airspeed decreases. Okay, and we can do this all day long. We can pitch up, pitch down, increase our angle of attack, decrease our speed, and vice versa. And so if we ever need airspeed, we know where we need to go. We need to go usually to the stick. The stick will give us airspeed. Now the question is that enough? It depends. Okay, but if I'm at 100 miles an hour here and I want to go to 80, there is some amount of back stick travel that I need to make to get to 80. And once I get there, I find that spot. I'm trying to find that new position in the controls that gives me 80. And if I want to go 100, there's some position forward of where I've just been, which is going to give me 100. And I'm trying to find that position in the controls, and I intuitively know where it is. Faster is out in front of me, slower is back towards me. If I want to go 120, keep the engine from racing here. There's some forward position of the stick that is going to give me 120 miles an hour. And there it is. I've found that position. Now, let's go find the 60 mile an hour position. So we're going to go from 120 down to 60. Well, I know that's back. I have to pull back on the stick. I'm trying to find that position. I'm pulling, I'm slowing down. And as I get close, I stop pulling because I know it's going to drop just a little bit more, and then I can just pull just a tiny bit. And there we go. I've just found the 60 mile an hour position in the stick. Okay? So, if you're trying to control airspeed, you know where you need to move the stick. Now the interesting part about it, I'm going to make a left turn here, clear left, turning left, is that the faster you go, the smaller this input gets on the stick. And if you go look into the physics and the equations, it falls right out of the equations. It's pretty cool. But when we're slow, it takes a lot of stick travel to cause a change in airspeed. And that's why, if you're flying a jet, it seems like you don't have to move the yoke at all to speed up or slow down the airplane. But to go from 400 miles an hour to 450 miles per hour is just, I mean, it's a sliver of an inch that you're moving that yoke forward to do that. And you barely even see it because the autopilot handles it, and you have to, we'll get to the power in a minute, but the power is going to change. But the airplane accelerating happens through just a tiny forward travel of the stick, versus to induce a change here in the Luscombe on the slow end of the spectrum, I have to make big inputs in the stick. There we go. So I have had to bring the stick back a lot to do this. And there we are at 40. I can bring the stick back about another inch, and the airspeed drops off a lot. Now if I want to increase, I got to really move the stick forward. You probably saw the stick come forward. Getting hazy here. I'm going to come down a little bit. Looks like we might have a little bit of a cloud layer above us, so we'll come back down to 3,000. Work our way down there roughly. As I move the stick forward and the airspeed increases. Okay, so I think I've beat this subject of airspeed control to death. And you need to just go out and practice changing your speed and holding your speed by just moving the stick. Now, let's come down to 3,500 feet, and we're going to do the next experiment, which is going to tell us a lot about any one particular airplane's behavior. So we're going to come down to 3,500 feet. We're going to trim the airplane for, say, about 90 miles an hour works. Okay. Say 85, and it's very important that we get the airplane just perfectly trimmed, and we know what it's trimmed for here, and I'm looking for 3,500 feet and 85 miles an hour. Okay, now we are going to induce a single change into the controls with a power increase. And the first thing we're going to do is we're going to look to the airspeed to see what happens to the airspeed when I make a power change. So I will keep the wings level, I'm going to keep the ball in the middle, but I'm not going to make any stick inputs. Let's see what happens. There was a slight increase, and now we get a severe decrease in the airspeed. Okay, this is going to set up a little bit of an oscillation, so I'm just going to tap it back to help it kind of seek its new norm. Otherwise, we're going to have to go through a couple pitch oscillations here to get to it. But I think we're going to see here, I've let go of the controls, that just changing the power induced about a 10 mile per hour decrease in airspeed. Now, does that make any sense at all? No, at first glance you would think if I increase the power, the airplane's going to accelerate. Well, it didn't, and we just proved it. Now, if we go back and reduce power below where we had it, we're going to see something quite interesting. We're going to see the nose drop, and we're way past 85 now, through 95, coming up on 100. I'm going to tap out the oscillation, and we're going to see that we're now doing 100. Keep the ball in the middle. And you may say, oh, that was a fluke, Dave. How can that be? Well, let's prove it by starting back where we were. So we're going to set that medium power. We're going to come back to 85 miles an hour. And now we'll induce the same change, reduction of power, and see what the airplane does. Okay, so we're back at 85. And now we reduce power. And there we get it again. We get the increase in airspeed, right? We're just trying to look at airspeed here. Now, the crazy thing about this is if you go do this test in different airplanes at different speeds, you are going to get different results. There are airplanes that will accelerate when you add power, and they will decelerate when you reduce power. There are airplanes that will do very little to the airspeed when you make a power change. There are airplanes that will behave just as this does, where the power does the opposite of what we want. And why is this? How could this be the case? This is so strange. Well, first of all, let's not get too far from home. I'm going to make a U-turn here. Clear left, turn and left. It's because airplanes configure their wings, their control surfaces, and their engines in different locations. That is the primary reason why. And so you can even get similar behavior for different reasons. I'm not going to get all into the gist of this, but this is something you need to know about a particular airplane if you're out flying it. What is the first behavior of the airplane when I make a pitch change with the stick and when I make a power change with the throttle? And let's answer the question of why this happens for an airplane with an engine out front and a tail in the back. It's primarily because, this is not the only reason, the primary reason is that when we change the power, we're changing the airflow over the tail. And so we're here at 85 and trimmed, and if I add power, I'm now blasting more air over the tail, which gives the tail more effectiveness, and now it was pulling down a little bit, now it's pulling down harder, which now induces a slight angle of attack change on the wing, and we get a steady change in angle of attack of the airplane, which then affects the airspeed. The same works in reverse. If we take out the power, we're taking away effectiveness from the tail, we're giving it less air, and now the tail has less effect, and it creates less downward lift, maybe even positive lift, and it tips the nose over, which then induces a negative or a reducing of the angle of attack of the wing. Crazy stuff. So this is all angle of attack driven, right? So what this really gets down to is something that I like to call a flight condition. What is a flight condition? A flight condition is a unique combination of airspeed and altitude. Specifically, not necessarily our altitude, but our vertical speed or our path through the sky, right? So right now we're on a level path, even though the vertical speed hasn't caught up to that reality. We're on a level path at about 82 miles an hour. That is a unique flight condition. They are one and the same, okay? Now, if I increase power and the airplane climbs at a slower speed, well, now my flight condition is, say, 75 miles per hour and a climbing path. Okay, those two things go together. So if I now reduce power, but I keep the airspeed at 75, which I didn't do. Try a little harder here. Now we have a different flight condition because even though the airspeed is the same, the vertical path is now different. Okay? And here's the moral of the story. You need to know intuitively what power you need for any given flight condition. And this is fairly simple, right? The faster we go, the more drag we create, the more power we're going to need. The steeper we want to climb, the more power that requires, right? The steeper we want to descend, the less power that requires. And so we need to have in our mind, I'm in this flight condition, I want to go to this flight condition. What power do I need to be able to do that eventually? So all that should really work out to is, do I reduce power? Do I keep it the same? Do I increase it, right? That's really all we're trying to get at here. So if I'm here in level flight at 80 miles an hour and I want to go faster level flight, well, the airspeed changes, the flight path stays the same, but I know because my drag increases, I'm going to need more power. So the first thing I do whenever I make a change from one flight condition to another, and this is where we get into, can you simultaneously control airspeed and altitude? Most pilots can control one or the other at any given time, but they can't control both. And we need to be able to control both. If we want to change the flight condition, we know that to accelerate in level flight, we're going to need more power. Now, does power accelerate the airplane? Well, we already answered that question. No, it doesn't, right? We've already demonstrated that. If I add power, I know the airplane's going to slow down. It's going to try and climb. But that then allows me to push forward and accelerate. The airplane is accelerating because I'm pushing forward on the stick. Right, we know I could go 100 without adding power. We would just start a descent, and that would be a different flight condition. So here's the revised rule of thumb. The first thing you do is you apply power for flight condition. Do I need more power, the same, or less power to go from what I'm doing now to what I want to do in the future? You then make that power change. Then, once you make that power change, then you can pitch for airspeed. So that's the revised rule, the causal rule. The first thing we do is we apply power to make the change in both airspeed and altitude that we want, and we then pitch to make that a reality. We make that pitch in our visual picture over the nose and in reference to the airspeed indicator. And with that rule, you can control pretty much any airplane. Any airplane I've ever flown, this will work. Now, you also want to go out and do the experiments which we've done of what happens when we make pitch changes, what happens when we make power changes in isolation, so that you can learn that behavior and you can consider that. But this is going to ring true. So I'm going to turn to the north, clear left, turning left. So let's say we're here at 90 miles an hour and 3,000 feet. If I want to slow to 60 miles an hour, I know that I'm going to need less power because I'm going to have less drag, because 60 miles an hour is pretty close to my best glide speed. So I'm going to have to reduce power, and there's going to be some power setting that's going to give me level flight at 60 miles an hour, that combination, right? And I'm going to just guess that it's going to be 1500 RPM. So I'm going to apply the rule. I'm going to set 1500 RPM. And then I'm going to do what we call locked altitude. And I'm going to just pitch back just fast enough to keep that altitude right locked on. And that will allow the airplane, as I pull back, to slow down. As I approach 60 miles an hour, I can then trim. And then I can ask, can I maintain 60 and hold altitude? That's now the question of the moment. And it doesn't look like it. It looks like I need just a little bit more power, maybe 1700 RPM. Okay, and now I just made a very smooth transition from 90 miles an hour to 60 miles an hour while maintaining altitude. Now, if I want to go back to my previous flight condition of 90 miles an hour, well, I know that needs more power for the airspeed and the drag, and so that I can then set that power. We'll say right about there. Now I lock my altitude in, which then allows the airplane to pitch forward without losing any altitude or gaining any altitude. I then start trimming. Start coming up on the airspeed. There's 90. And I don't think I quite needed as much power as I estimated, but that's the whole point, is that you make the guess in the right direction, you fine-tune it later. Okay? Now, we talked about the exercises to determine how the airplane is naturally going to respond. We change one or the other, and we let it settle. The next thing we need to do is practice locking things. And there are three things that we can lock. We can lock our airspeed, we can lock our altitude, and we can lock our vertical speed. And locking airspeed and altitude at the private level is critical. Locking vertical speed is critical at the instrument level. So today we're just going to talk about airspeed and altitude. So one of the exercises that I like to do with my students is I like to say, okay, we're here at 95 miles an hour. I'm going to change the power, and I want you to keep 95 miles an hour. No matter what, whether we're climbing, descending, level, whatever, keep 95 miles an hour. So then in the right seat, I would then start messing with their power. I would take the power away, and then the airplane's natural behavior is going to kick in. I'm going to have to let the nose down a little bit. I'm already behind the ball a little bit. And I'm trying to pitch and find the pitch attitude and the trim that holds 95. There it is. And then without them expecting it, I might add power. They now then have to ride through the transition. The airplane wants to slow down a lot. I'm showing how rusty I am here. Yep, I raised the nose too much. And now they have to try and hold 95. Another power change. And so we should, as pilots, be able to keep the airspeed needle locked in when the power changes. So now I'm going to take power out. I know I'm going to have to just nudge the nose down to find that new flight condition. There we go, and I'm doing better this time. We made it up to the Platte River here. So there's 95. I increase power. I'm going to have to raise the nose just a little bit, not too much. There we go, and I'm able to keep 95. And then I might say, okay, now go to 70. Okay, so then we got to raise the nose. I'm looking outside. I lock in a picture over the nose. I let the airspeed decelerate. The airplane approaches 70. I had the nose up just a little too much. And there's 70. And then I mess with the power. I take the power away. Well, they're going to have to pitch over to keep that, but not too much, which I just did. I pitched too much. And I can come back on 70. Add power. To be able to keep it on 70. There we go. Okay, so that's a really good exercise you can do, is locking the airspeed. Now, we can also lock the altitude, like I said, and locking the altitude is really good for changing the airspeed. So if I want to accelerate, well, I'm going to lock altitude by keeping the altitude in place, and by pushing forward, the airplane will accelerate. I'll allow it to accelerate. There we go, so I'm keeping us at 30-50. And that allows the airspeed to change. So basically, if you lock one of these, the other one is going to change. Okay, and so there we are. I've locked the altitude and the airspeed increased. Now, if I lock the airspeed here at 100 and I decrease the power, well, now I know that my airspeed is going to change. So we can control one or the other at any given time. Or we can lock one and the other one can change, right? So this is one of the big issues that I see. We're coming into the traffic pattern and we're, say, doing 100 miles an hour. I'm going to make a U-turn here. Clear left, turn left. We're coming into the pattern at, say, 100 miles an hour, and it's time to slow down to, let's just say, 70, right? But then it's also time to, say, go down, right? We need to start down at the numbers. And so then it's like, wait, which one am I going to do? Am I going to pitch, or am I going to power, or what am I going to do? Well, we know that to go from 90 level to 70 descending is going to be less power. And we want to slow down as well, too, because we don't want to get fast in the descent. And so what I would be looking for is that we're, say, let me get us right on 3,100. The cleanest transition would be to apply our rule. First, apply power for flight condition, then pitch for airspeed. And so here we are. We'll call it 90 miles an hour and 3,000 feet. Okay, we want to slow down and go down. Let's say we want to go down at 60. Okay, well, the first thing I'm going to do is I'm going to make a power change to get to the new condition. I'm going to lock my altitude, which allows the airspeed to change. I'm trimming back, I get to 60, and now I let the nose down just a hair to keep 60, and now we're going down. That is the cleanest, smoothest transition you can do from level flight to descending flight at a slow airspeed. And that is the hard one. Slowing down and going down at the same time. It's easy to accelerate and go downhill. It's harder to slow down and then go down. So sometimes you get competing goals, right? Slowing down and going down. They're usually competing. And so you got to be able to cleanly say, all right, where does my power need to go? What do I need to do with my pitch to get the airplane to lock into the airspeed and vertical profile that I want it to? And so what this is really saying, and this is where the phrases like pitch for airspeed, power for altitude fail, is that they're trying to apply a single control to a single output. Unfortunately, life is not that simple. Unfortunately, airplanes are not that simple. Instead, we have what I like to call, or what an engineer might call, a multi-input, multi-output system, which means that we have multiple ways of changing the same thing, and that multiple things can affect other things. And so then, if this really is, if an airplane in level flight is a multi-input, multi-output system, you cannot create a statement with a single cause and effect, because it just simply will not work. The physics will not agree with that. Okay, so we have to accept the nuance that both affect both to some extent, right? We've seen that if we make airspeed changes, we get flight path changes, right? I push down, the airplane accelerates. I pull back and slow down, the airplane can climb, right? If I make power changes, I can affect airspeed and I can affect altitude, right? So we're again at 3,000 feet, 85, I take power away, I can induce an altitude change and an airspeed change, right? Multi-input, multi-output. And once you see that, then it starts to make a little bit more sense. But I think you'll find that the statement, power for flight condition, then pitch for airspeed, will help you a lot. So we're going to start working our way back to Wahoo here, and we'll get the weather.
Air 70. Wahoo Municipal Airport. Automated weather observation 1409er. Zulu weather. Wind 040 at 12. Visibility 10. Ceiling 3,200. Broken temperature 14 Celsius. Dew point 8. Altimeter 29er 70. Wahoo Municipal.
Okay, we've got the radio set up for the return. I'm going to make a call. Wahoo traffic, Luscombe 77903 is 10 miles to the northwest, inbound 02 Wahoo. Okay, so let's work through a transition here. It's fairly smooth, so we're going to go ahead and head down to pattern altitude. So I'm at 92 miles an hour and 2,900 feet. I need to get down to 1,200 feet. Or, sorry, 2,200 feet, which is 1,000 feet above the ground. And I like my speed, so I know that to go down, I'm going to need less power. So I reduce power. I can then apply just a hair of back pressure and a little spin of trim to keep us here at 95. And the airplane goes down. Okay, when I get to 2,200 feet, I'm going to want to return to level flight and maintain airspeed. So I know I'm going to need more power. So I'll make my power change, and then I'll keep the airspeed locked in and make a slight pitch change. And so, right, what I mentioned earlier in the video, different airplanes, right? And different airplanes, like I said, respond in different ways, right? And like for example, one of the jets that I fly, if you add power, the engines are mounted high, and actually push the nose over. And so you add power, the airplane accelerates. And that gets to kind of one final thing, getting back to the multi-input, multi-output thing that I was getting at earlier. And here we come up to 2,200 feet, is that there are really two ways to accelerate an airplane. If we can put thrust on the nose, we can make the airplane accelerate. And we have two ways of doing that. The first, of course, is the engine. So we can add thrust, and that will then allow us to accelerate the airplane. Now we know in this particular airplane that's going to have a big effect on the tail, which we're going to have to counter with the stick to keep the trim where we want it. But like I said, in my jet at work, you add power, it pushes the nose down because the engines are above the center of gravity, and they're also adding thrust on the nose. The other way we can put a force on the nose is gravity, right? And so if I push the nose down and I put gravity closer to under the nose or towards the direction we're going, the airplane's going to accelerate. And that's kind of the core tension, if you will, that frustrates people with airspeed and altitude, is that there's more than one way to skin the cat, right? Anywho here, so we're coming back into Wahoo. We're just sitting right above 2,200 feet. I'm back at my 90 to 95 miles an hour with a little bit of added power. My fuel looks good. Looking around for other airplanes. Let's talk about our pattern entry plan. So we're using runway 02. So I'm going to come in. I'm basically set up on a perfect 45 entry into the downwind to make left traffic for 02. So you really couldn't ask for an easier pattern entry. So our thinking ahead, our next call is going to be our 5-mile call. And we're coming up on that here shortly. But yeah, back to pitch and power. We have two ways of putting a force on the nose, both the thrust from the engine and the and gravity. And so it complicates things. But the things you can do to improve is to go out, trim the airplane up, make isolated inputs on the stick and on the throttle, see how the airplane behaves, and then practice locking one versus the other, right? It's impossible to always just absolutely perfectly lock both, right? So if we're here at just a little bit high and on speed, I can't make both do what I want always at the exact same time, right? So if I'm here at 2,200 feet, I don't want to make a power change to get back down because I'm 75 feet high. So in this case, I know that if I pitch, I'm going to increase airspeed slightly. Oh, and I'm willing to do that because I can get away with just 2 or 3 miles an hour here of extra speed, and I can come back down. I get to 2,200 feet, I raise the nose, the airplane slows back down. And so when you're in level flight, right, you can pitch for altitude. That's fine. And that would go against the classic pitch for airspeed, power for altitude statement, right? Because we only are supposed to pitch for airspeed, right? But that's just not the case. It is okay to make slight airspeed changes to make an altitude change. You don't have to just fly the altimeter needle with the power. But you're going to sacrifice one for the other. The question is, are you doing that cleanly? Are you doing it efficiently? Are you doing it without fighting the airplane? And that's what I see a lot, is a lot of fighting the airplane, right? We're trying to...
Laverne traffic, Departure 28 November Sierra, inbound for pattern work for runway 36. Going to be entering a left downwind, Laverne, 2 miles out.
And they're trying to slow down and go down, and they speed up to go down, and then they try to slow down, and then they go up, and it's kind of this back and forth here. So let's make another call. Wahoo traffic, Luscombe 77903 is 2 miles northwest, 45 entry, left downwind, 02 Wahoo. But remember the rule. Power for flight condition, then pitch for airspeed. That will allow you to transition back and forth between the two. We know that the primary control, or the primary result of the stick is an angle of attack change, which then can induce an airspeed change. And that really the power is just adding or taking away energy from the whole scenario. We can then choose how to use that. We can choose to use it to go up. We can choose to use it to go faster. But our choosing happens with the stick. But first of all, we need the power there to be there if we need it. In that scenario. Okay, so we're coming into the 45 here. I'm going to make my downwind entry. Wahoo traffic, Luscombe 903s, joining left downwind 02 Wahoo. I'm a hair high, 85 miles an hour. I'm in the left downwind. My fuel's on. That's really all I have to do. I'm going to beam the numbers, carburetor heat. Alright, I need to slow down and go down, so I'm going to reduce the power to idle. Simultaneously bring the stick back to slow down. Get to 65, let the nose down just a little bit to keep 65. And 11. Wahoo traffic, Luscombe 77903, left base 02 Wahoo. Okay, we're on a left base. Looking down final. I don't see anyone. Looking at my windsock.
Here's 458 Charlie Papa, 10 miles to the south, inbound, RNAV 35, County.
Just a hair slow, I let the nose down. Now in this situation, I'm in a gliding situation, keeping my speed, which gives me a stable glide. And then I have to use other tools to arrive at the runway. The primary one is geometry. We'll talk more about that when we get to pattern lessons. We also have a slip, so I'm going to use a little bit of a slip here. There we go. So we're slipping, slipping, slipping. I look at the windsock, because we always look at the windsock each lap around the pattern. The windsock looks good. I'm doing 65. I like my speed. Coming down. Little pull, little pull. Oh, we might turn this into a 3-point. Yeah, it was kind of a 3-point. Okay, not quite slow enough to make the turn off there onto the other runway, so we got a ways to taxi. Now, why wouldn't I just do a U-turn and do a back taxi? That's a good question. It's actually something I used to do a lot. But if you read the FAA material, the FAA would prefer, I'm not saying we don't have to, but they're preferring that you don't back taxi if you have runway exits available in front of you. The theory is keep the flow of the airport going the way it's going. You know, and there are plenty of airports where there's Nordo traffic, and you know, you might get someone who's Nordo, no radio, right, and they are landing behind you, and you turn around, and for better or for worse, they're right in front of you, right? There's a lot of things that could, you know, that could go wrong, that could put you in a scenario like that, right? But right, we can only control our own behavior, right? If someone's landing Nordo right behind us, it happens. It's not a good thing, and but that doesn't mean that we can control them. So, hey, just roll it out. You're being predictable, and we're meeting the FAA guidance. Okay, Wahoo traffic, Luscombe 77903 is clear of 02, taxi to the hangars, Wahoo. Okay, so we taxied all the way down the runway, we made the turnoff. Also, hey, it saves the brakes, right? So, brakes on these old Luscombes are not like there's exactly replacement parts laying around at every AutoZone, so. Anyhow, so we're taxiing out here. And in one of my previous videos, I talked a little bit about brake failures. I said that we taxi slow because of a potential brake failure. And so I'd like to actually demonstrate that now. So let's say we had a right brake failure. So we apply the brakes and the airplane starts going left because the right brake failed. It will not function. So in that case, to come to a stop, we're going to need to apply left rudder, or right rudder and left brake. And I'm doing that now. Make a call. Wahoo traffic, 903's crossing 1331, Wahoo. And that is very difficult to discipline yourself to apply left brake and right rudder to keep the airplane straight while that happens. So that might be something you want to practice on a wide ramp someday, is braking and stopping with only one brake and opposite rudder. It's actually a lot harder than you might think. But I've had single-sided brake failures and had to use that before. And so it might be something you want to give a try. All right, I'm going to turn my fuel valve off now because I need to drain out the gascolator. In previous videos, I've mentioned this briefly, but I haven't expounded on it much. This old Luscombe has what's called a Stromberg carburetor and does not have a mixture control, right? We don't see a mixture here anywhere. And so we can't shut the airplane down with a mixture. We got to have some way to shut it down. And the theory goes that if you shut it down with the mags, you're still drawing in fuel and the engine's loaded up with gas. And so instead, we can turn the fuel valve off and slowly use up the fuel left in the gascolator, and the airplane will eventually die. So that's how I do it. My anecdotal experience is that when I shut down with the keys, it's a lot harder to restart, especially in hot conditions. It seems to kind of flood the engine out, so that's why I prefer turning off the fuel valve. I also think it seems to me to be safer to get rid of the fuel, right, than just to take away the spark, because you can always bring the spark back. And about to die here soon. There she goes.
All right, everyone, thanks for coming along on this flight. I hope you found it helpful in understanding how to control airspeed and altitude. And please like and subscribe, and we'll see you in the next video. Until then, fly safe.